first. So, okay. Hi, I'm Will Sutton.
I'm Annelise and Will.
Today we're going to be discussing implicit differentiation as an introduction to the topic of related rates, which describes quantities in motion and how they change. And finally, we will extend our discussion of related rates into some thought on parametric equations, which describe multiple quantities in motion as they relate to the real world. Implicit differentiation is an extension of the concept of the derivative into the realm of functions and equations with two variables, one of which is dependent. So our example here is the volume of Descartes, which has two variables, x and y, x being independent and y being dependent. Now, we could not differentiate this by normal means because we can't isolate y. We could never get this in explicit terms. So we do it implicitly. What this involves is treating x like you would treat any other independent variable and treating y as its own function. So when we're writing the derivative of this, we use standard differentiation to work with x, and when we differentiate y, every time we do that, we take the derivative of y and then we leave the term dy dx, standing for derivative of y with respect to x, or y prime. These two notations are the only way you can describe derivatives implicitly. So here's the process for actually differentiating the volume of Descartes. Beginning here with our original equation, we use the product rule to separate this side into 3y plus 3x y prime, and this side into 3x squared plus 3y squared y prime. Notice that when y is differentiated, we, instead of simply taking the exponent rule shortcut, we're actually left with y prime, its own function. And y prime becomes the variable that we're going to attempt to isolate, which we do in the following few steps through algebra as we separate y prime from the other parts and then divide out, giving us that y prime is equal to x squared minus y over x minus y squared. And this equation here describes the rate of change of the volume of Descartes. So implicit differentiation finds its real-world application in related rates, which basically takes this process and extrapolates it to real-world applications when we look at the way that things are changing in the world and try to model the rate of change of other things based off of those.
Related rates are used to describe geometry in motion. Using formulas we learned in geometry, like the Pythagorean theorem, volume and area of different shapes, we can describe the rate of one object as it relates to the rate of another object. For example, we can take the derivative of the volume of a cylinder, v equals pi r squared times the height, and take the derivative with respect to time. The derivative with respect to time of the volume, treating both r and h as their own functions, equals pi times the quantity 2r times the derivative of r with respect to t times h plus r squared times the derivative of h with respect to t.
So Mr. Torrey's cat here is sitting underneath a ladder that is sliding down the wall. Instead of going to rescue his poor cat, Mr. Torrey decides to sit down and do some calculus and figure out just how long he has before the cat is squished into oblivion. So we know that the base of the ladder is 10 feet away from the wall and that it's moving away from the wall at a rate of 4 feet per second, and that the entire height of the wall from the ground to the top of the ladder is 17.321 feet. And his cat's 2 feet tall, so that means that this distance here is 15.321 feet. And the ladder is 20 feet. So we want to know how fast this distance is changing from the top of the ladder to the cat in order to figure out how much time it has left. So we're going to begin with our Pythagorean theorem, c squared equals a squared plus b squared, pretty easy. And we're going to input some of our knowns and also differentiate. So we have 40 is equal to 2a, a being the base, times the derivative of a, plus 2b times the derivative of b, b being the height. So when we put in some of our knowns, we're going to have 40 equals 20 times 4 plus 2 times 17.321, which is roughly equivalent to 34.642, did that one in my head, and times b prime. And then we're going to do a little bit of more magic, so we're going to have 40, that's a 4, equals 80 plus this. We're going to do some n, we're going to subtract, so we have negative 40 equals, I got to put down, 34.642b prime, and we will divide, and we're going to get a value for b prime that equals negative 1.1547 feet per second. So this is the rate at which the ladder is moving down the wall, at which the distance is changing between the top and the bottom. Now, how are we going to figure out how many seconds this poor cat has left? It's simple. We take the height of the ladder between the ladder and the cat at the time, and we're going to simply divide it by the rate, and we're going to get that the cat has 13.2684 seconds left, which is just enough time for Tori to finish his calculus problem and maybe still save the cat.
Alright guys, next we've got this falling light graphic that we're going to show you. It's a related rate. As you can see, as the light goes down, the shadow moves up, and it's really complicated, but you know, I'm feeling a bit tired. I'm going to pull a substitute and just let you guys do it. Go on, do the calculus. Another example of related rates is this problem here, where we have two circles, one inside the other, and they're both expanding at different rates. The outer circle, R2, has a radius of 16 and is expanding at a rate of 1 centimeter per second. The inner circle, R1, has a radius of 5 and is expanding at a rate of 2 centimeters per second. In this case, we're looking for the rate of change of the area between the two circles. To start out, we have the area function just to find the area between the two circles, which is the larger area minus the smaller area. When you take the derivative of that, you get this function here, which describes the rate of change of that area as the circles are changing. These quantities, you have r of the radius of the bigger circle, and the rate of change of the radius of the bigger circle, and then the radius of the smaller circle and the rate of change of the radius of the smaller circle. When you plug in your values here and here, then you end up with the rate of change of the area being 37.699 centimeters per second. So now we're going to do an example problem with our Great America data. As you can see on this graph that I created, there are several sections that we had to put in here because our data is imperfect. First of all, you can see the blue rectangle, which represents the area of free fall from the drop zone ride. It's not exactly a rectangle in the graph. As you can see, there's some static in there, but this is what it should look like. We know that the acceleration due to gravity is negative 9.8 meters per second, and then we know that the duration of the free fall is about 3 seconds. So we figured that we have 29.4 meters per second of velocity during that time period. Therefore, we know that since we came to a stop at the end of the ride, that the braking, which you can see is an upward trend over here, needs to actually be longer and higher. So I put in this little extra bit, and it turns out that we need to have about 18 meters per second of positive acceleration in order to bring us to a complete stop with this time period of braking.
So this triangle models the drop zone ride at Great America as it falls. You can see we have a person on the left observing the angle and a person on the right riding the terrifying ride of death. So x is our distance between the observer and the base of the ride, given by 92.66 meters. Y is the height of the ride at a specific moment. For this, it is the instant in which free fall ends, 46.7248 meters. And z, the hypotenuse, calculated by the Pythagorean theorem, is 103.7742 meters. So what we want to find is the rate at which the distance z between the observer and the falling ride is changing at the exact moment that free fall ends.
Alright, these are our givens. As you can see, x equals 92.66 meters, and we found that theta was 26.76 degrees. Using this and this, we were able to calculate y as being 46.7248 meters, and using these two values, we could calculate z, which is 103.7742 meters. We also know that x prime is 0 meters per second because x is not changing, and y prime is negative 29.4 meters per second. Alright, so to find our rate of change of z, we use the version of the Pythagorean theorem. Here we have z squared equals x squared plus y squared. We use these values because x is the distance from the observer to the ride, and y is the height of the ride. Therefore, z is the hypotenuse. which is what we're looking for. Okay, so we took the derivative with respect to time and came out with 2z prime equals 2x prime plus 2y prime. Then we isolated z prime here. Once we plugged in our values, which we already demonstrated over here, we ended up with z prime equaling negative 13.2375 meters per second. Okay, so to wrap up our Great America project, z prime is the change in distance between the observer and the ride. This number should be negative and less than the speed of the falling ride, which it is. So this number, the negative 13 point whatever, actually makes sense. Also, it is worth noting that when we calculated the height of the ride, which is y, we accounted for the height of the person measuring the angle. This ride is actually about 2 meters taller, but in these calculations it doesn't really affect our numbers that we got.
So the following is an extension of the derivative and related rates into the world of parametric equations. So a parametric equation is a function or an equation that's given by two variables, x and y, when x and y are their own functions. Specifically, x is called f of t and y is called g of t, when t is what's called the parametric variable, which can be time or anything else, but basically that describes how the two variables change independently and then their outputs are graphed to form a parametric graph. So parametric equations also have derivatives, which describe the rate of change. And the derivative is given by calculating both the derivative of the y function and the x function. So the derivative of a full parametric equation in standard form is dy dt over dx dt, which is basically the rate of change of y over the rate of change of x, both with respect to the parametric variable t.
Okay, so for our parametric example problem, we are going to use chemistry. So in this problem, a mad scientist is doing an experiment with two different solutions. So as you can see here, each of the solutions, x of f and y of f, are dependent on a temperature in Fahrenheit. That's why we used f. So x and y are parameters which describe c of t, the parametric equation, which in turn describes the amount of solution produced when these two solutions are mixed. C of t depends on t indirectly, because each variable, x and y, is dependent on f, as you can see here. And f is dependent in part on t. It's kind of like dependencyception. Then, as you move on to taking the derivative, you find that dc dt equals this, in which case x and x prime are represented by this function and the function's derivative, and y and y prime are also dependent on y and its derivative.
Go.
Now we're going to find out what the rate of change of c is when the instantaneous temperature of f is equal to 2 degrees Fahrenheit and the change in temperature is 6 degrees per second. Okay, so now taking our derivative of c of t function and plugging in our values, 2 and 6, we get this mess, which in turn equals 1,499,136, and we decided it must be in milligrams because that's a ridiculously large number, which in turn equals 1.499 kilograms. At that point, the product gained consciousness and left the lab.
Somebody asked me once, why do we learn all these things in calculus? What is the point? So I think related rates is a beautiful example of why we learn calculus, what calculus can do for us. As illustrated by the problem with the monster, we can figure out how things in the real world behave and how they react to one another based on their rates of change, which is something we can only do through related rates. So those allow us to examine quantities in motion, as you might recall, and how they relate to one another, just like geometry in motion. So next time you find yourself wondering, why am I learning this? How does this apply? Just think that it could have been you.